Magnets surround us everywhere we look. They hold our shopping lists to refrigerator doors, power the speakers in our headphones, and guide compass needles toward magnetic north. But step outside our everyday world, and magnetism becomes even more extraordinary. The sun generates magnetic fields millions of times stronger than Earth's. Entire galaxies stretch across space, threaded with invisible magnetic highways that guide charged particles across distances so vast they boggle the mind. Yet here's the fascinating question that keeps scientists awake at night. Where did the very first magnetic fields come from? Long before planets formed, before stars ignited, before galaxies even existed, the universe was nothing but a hot, glowing soup of particles. No iron cores spinning inside planets, no solar dynamos churning in stellar interiors, just pure energy and matter in its most primitive form. So how did magnetism first spark into existence? This isn't just idle curiosity. Understanding the birth of magnetism means understanding something fundamental about our universe itself. Every magnetic field we see today, from the weakest refrigerator magnet to the most powerful galactic field, can trace its ancestry back to those first primordial magnetic moments. The answer lies in a beautiful principle of physics. Magnetic fields always, without exception, arise from electric charges in motion. When electrons flow through a wire, they create magnetism. When plasma swirls inside a star, magnetic fields emerge. Even the tiny spinning motion of individual electrons generates the magnetism we find in iron and other metals. But in the early universe, we had something special. We had a cosmos filled with hot, ionized plasma, where electric charges moved freely in ways impossible today. The conditions were perfect for magnetism to be born, but the exact mechanism remains one of science's most intriguing puzzles. Multiple theories compete to explain this cosmic birth story. Some point to quantum fluctuations stretched across space during the universe's explosive first moments. Others suggest that as fundamental forces froze into their current forms, temporary imbalances created the first magnetic seeds. Still others propose that natural plasma processes, the same ones we can create and study in laboratories today, generated those crucial first fields. To understand which theory might be correct, we need to start from the basics. What creates magnetism at all? How do moving charges become invisible fields that can reach across empty space? And once we grasp these fundamentals, we can journey back to the very beginning of time itself to witness magnetism's first spark in the infant universe. To understand how the first magnetic fields emerged from the primordial universe, we must first grasp a fundamental truth about magnetism itself. Every magnetic field that has ever existed, from the weakest compass needle to the most powerful galactic dynamo, follows one unbreakable rule. Magnetic fields are always, without exception, generated by electric charges in motion. This isn't just a convenient approximation or a simplified explanation. It's an absolute law of physics, as reliable as gravity pulling objects toward Earth or light traveling at 300 million meters per second. No magnetic field has ever been found that violates this principle. No magnetic monopole, no isolated magnetic charge, no magnetic field appearing from nothing has ever been discovered, despite decades of searching by the world's most sophisticated experiments. The relationship between moving charges and magnetic fields was first discovered in 1820 by Danish physicist Hans Christian Ørsted. He noticed that electric current flowing through a wire could deflect a nearby compass needle. This simple observation revolutionized our understanding of electromagnetism and laid the foundation for everything from electric motors to magnetic resonance imaging machines. What Ørsted discovered was that electricity and magnetism are not separate phenomena, but two aspects of a single electromagnetic force. Let's explore what this means in the world around us, starting with the most familiar example. Consider Earth's magnetic field, the invisible shield that protects us from harmful solar radiation and guides migrating birds across continents. This field extends far into space, creating a protective bubble called the magnetosphere that deflects most of the charged particles streaming from the sun. Deep beneath our feet, roughly 3,000 kilometers down, lies Earth's outer core. This region contains liquid iron heated to temperatures exceeding 5,000 degrees Celsius, hotter than the surface of the sun. The iron doesn't just sit there motionless. It churns and flows in complex patterns driven by Earth's rotation and heat from the planet's interior. The physics of this process involves multiple interconnected mechanisms. Heat from Earth's solid inner core creates convection currents in the liquid outer core, much like hot air rising from a radiator creates circulation patterns in a room. But Earth's rotation adds a crucial twist to these convection patterns through something called the Coriolis effect. The same force that curves hurricane paths and affects ocean currents also influences the flow of molten iron 3,000 kilometers beneath our feet. As this molten iron moves, it carries electric charges with it. Iron atoms in the liquid state have lost some of their electrons due to the extreme temperature, creating a mixture of positively charged ions and freely moving electrons. This hot, electrically conducting fluid is essentially a plasma, similar to the material that makes up the sun's interior. When this electrically conducting fluid flows in organized patterns, it generates electric currents on a planetary scale. These enormous currents flowing through thousands of kilometers of liquid metal produce Earth's magnetic field through a process scientists call the geodynamo. The currents form complex loops and spirals, creating a magnetic field that resembles a giant bar magnet tilted about 11 degrees from Earth's rotational axis. The geodynamo is not a simple, steady process. Earth's magnetic field fluctuates constantly, sometimes weakening, sometimes strengthening, occasionally even flipping completely, so that magnetic north becomes magnetic south. The geological record preserved in ancient rocks shows these reversals have happened hundreds of times throughout Earth's 4.5 billion year history. Some reversals occur gradually over thousands of years, while others might happen much more rapidly. During a reversal, Earth's magnetic field doesn't simply flip like a switch. Instead, it weakens dramatically, sometimes to just 10% of its normal strength, and the magnetic poles wander erratically before settling into their new positions. The magnetic field might even develop multiple north and south poles temporarily. These chaotic periods could last anywhere from a few thousand to tens of thousands of years. Yet through all these changes, the underlying principle remains the same. Moving electric charges in the liquid iron core create the magnetism that surrounds our planet. The complexity arises from the intricate fluid dynamics of the outer core, where rotation, convection, and electromagnetic forces interact in ways that scientists are still working to fully understand. Now consider a simple bar magnet, the kind you might stick to your refrigerator. At first glance, it seems to contradict our rule. The magnet isn't obviously moving, and you can't see any electric currents flowing through it. Where are the moving charges that create its magnetic field? The answer lies in the quantum world of atoms and electrons. Every electron possesses a property called spin, which you can think of as the electron rotating around its own axis like a tiny spinning top. This spinning motion creates a microscopic electric current, and that current generates a small magnetic field around each electron. But electron spin is actually more subtle than simple rotation. It's a purely quantum mechanical property that has no direct analog in our everyday experience. An electron doesn't literally spin like a planet or a ball. Instead, spin represents an intrinsic form of angular momentum that the electron carries, somewhat like how mass represents an intrinsic property of matter. In most materials, electrons pair up with their spins, pointing in opposite directions, cancelling out each other's magnetic effects. This pairing occurs because of another quantum mechanical principle called the Pauli exclusion principle, which prevents two electrons from occupying exactly the same quantum state. When electrons pair up with opposite spins, they can occupy the same orbital around an atomic nucleus. But in ferromagnetic materials like iron, nickel, and cobalt, something special happens. The atomic structure and electron configuration of these elements allows unpaired electrons to align their spins in the same direction across large regions of the material called magnetic domains. These domains can contain billions upon billions of atoms, all with their electron spins pointing the same way. Within each magnetic domain, quantum mechanical interactions called exchange forces cause neighboring electrons to prefer having their spins aligned parallel to each other. This preference for parallel alignment overcomes the thermal energy that would otherwise randomize the spin directions. The result is regions of the material where enormous numbers of electron spins point in the same direction. When billions upon billions of electrons all spin the same way, their individual magnetic contributions add up to create the strong, permanent magnetic field we observe. A typical refrigerator magnet might contain magnetic domains with trillions of aligned electrons, each contributing its tiny quantum mechanical magnetic moment to the overall field. The boundaries between magnetic domains can move when external magnetic fields are applied, allowing the material's overall magnetization to change. This is why you can magnetize a piece of iron by stroking it with a permanent magnet, and why magnetic materials can be demagnetized by heating them above a critical temperature called the Curie point. So even in a simple bar magnet, the fundamental principle holds true. Moving electric charges, in this case spinning electrons, create the magnetic field. The motion happens at the atomic level rather than the macroscopic level, but motion it remains. Let's scale up dramatically and consider galactic magnetic fields. The Milky Way, our home galaxy, possesses a magnetic field that extends across its entire 100,000 light-year diameter. This field, though incredibly weak compared to Earth's field, plays a crucial role in galactic evolution. It channels the flow of cosmic rays, influences star formation, and helps shape the spiral arms we see in many galaxies. The strength of galactic magnetic fields is typically measured in microgauss, roughly 1,000,000 times weaker than Earth's magnetic field. To put this in perspective, if Earth's magnetic field were represented by a gentle breeze, galactic magnetic fields would be like the barely perceptible movement of air in a perfectly still room. Yet despite their weakness, these fields extend across such vast distances that their total energy content is enormous. How does such an enormous magnetic field arise? Once again, moving electric charges provide the answer. Galaxies contain vast quantities of ionized gas called plasma. This plasma consists of free electrons and atomic nuclei that have been stripped of their electrons by high-energy processes like stellar radiation, supernova explosions, and collisions with cosmic rays. As galaxies rotate, differential rotation causes this plasma to move in complex patterns. Different parts of a galaxy rotate at different speeds, just as different parts of a whirlpool in water move at different rates. The inner regions typically rotate faster than the outer regions, creating shearing motions in the galactic plasma. These shearing motions, combined with turbulence from stellar explosions and other energetic events, drive electric currents through the galaxy on scales of tens of thousands of light years. The process is remarkably similar to Earth's geodynamo, but operating on scales that dwarf anything in our terrestrial experience. Galactic dynamos operate on timescales of hundreds of millions of years. They can amplify weak seed magnetic fields by factors of millions or billions, transforming barely detectable primordial fields into the substantial galactic magnetism we observe today. The process involves the complex interplay of rotation, turbulence, and plasma physics, but the underlying principle remains unchanged. Moving charges create magnetic fields. This brings us to a crucial realization about the early universe. 13.8 billion years ago, when the cosmos was young, hot, and dense, none of these familiar sources of magnetism existed. There were no planets with molten iron cores spinning in space. No stars had yet formed to create the heavy elements needed for ferromagnetism. No galaxies had assembled to host the large-scale dynamos we observe today. Instead, the early universe was filled with a hot, ionized plasma at temperatures of billions of degrees. In this plasma, electrons and atomic nuclei moved freely, unbound by the cooler conditions that would later allow neutral atoms to form. This primordial plasma was a perfect conductor of electricity, with charged particles able to move with almost no resistance through the fabric of space-time itself. The question becomes, what could have caused these charges to move in organized ways that would generate magnetic fields? Random thermal motion alone wouldn't suffice. For magnetic fields to emerge, there needed to be systematic, coherent motions of electric charges across large regions of space. The early universe lacked the familiar astronomical objects we see today, but it possessed something equally important for magnetogenesis. It had the raw ingredients, the extreme conditions, and the dynamic processes necessary for magnetism to emerge from pure physics. The challenge for scientists is determining which of these processes actually operated and left their magnetic signatures in the cosmos we observe today. Picture the universe at the most extreme moment in its history. We're not talking about the Big Bang itself, but something even more dramatic that happened in the first tiny fraction of a second afterward. Between 10 to the minus 36 seconds and 10 to the minus 32 seconds after the Big Bang, the universe underwent a period of exponential expansion called cosmic inflation. During this unimaginably brief moment, space itself expanded faster than the speed of light, growing by a factor of at least 10 to the 26, and possibly much more. To grasp the scale of this expansion, imagine a region of space smaller than a proton suddenly inflating to the size of a grapefruit in less time than it takes light to cross the nucleus of an atom. The entire observable universe today, with its hundreds of billions of galaxies spread across nearly 100 billion light-years, may have originated from a region smaller than the period at the end of this sentence. This cosmic inflation wasn't just empty space expanding. The fabric of space-time itself was stretching, carrying along with it any physical fields that existed at the time. Among these fields were the electromagnetic fields that would eventually give rise to all the magnetic phenomena we observe today. But at this primordial moment, these fields existed only as quantum fluctuations, the ghostly variations in energy that quantum mechanics tells us must exist even in completely empty space. Quantum mechanics reveals that even perfect vacuum isn't truly empty. It seethes with virtual particles and field fluctuations that constantly appear and disappear on timescales, so brief they barely qualify as existing at all. Under normal circumstances, these quantum fluctuations remain microscopic and undetectable, but cosmic inflation changed everything. As space expanded exponentially, these tiny quantum fluctuations in electromagnetic fields were stretched along with space-time itself. Fluctuations that began smaller than the Planck length, the smallest meaningful distance in physics, were inflated to macroscopic scales. What started as quantum whispers became cosmic shouts, imprinted permanently into the structure of the expanding universe. This process, known as inflationary magnetogenesis, represents one of the most elegant explanations for how the first magnetic fields could have emerged from pure physics. No complex astrophysical processes were needed. No dynamos, no plasma instabilities, no moving charges in the conventional sense. Just the fundamental properties of quantum fields interacting with the explosive expansion of space-time itself. The mathematics of inflationary magnetogenesis involve some of the most sophisticated concepts in theoretical physics. The key insight is that electromagnetic fields, like all quantum fields, are subject to uncertainty relationships that prevent them from having precisely zero energy, even in vacuum. These zero-point fluctuations normally cancel out over large scales, but inflation preserves and amplifies the fluctuations that happen to exist during the inflationary epoch. However, there's a significant technical challenge that makes inflationary magnetogenesis more complex than it might first appear. The standard equations of electromagnetism, known as Maxwell's equations, possess a mathematical property called conformal invariance. This means that electromagnetic fields are not naturally coupled to the expansion of space in a way that would allow inflation to amplify them. To understand why this matters, consider how different types of fields respond to cosmic expansion. Some fields, like those responsible for matter density fluctuations, are naturally stretched and amplified by inflation. But electromagnetic fields, in their standard form, remain essentially unchanged by the expansion of space. It's somewhat like the difference between stretching a rubber sheet with patterns drawn on it versus stretching a sheet of glass, where the patterns remain the same size relative to the material. For inflationary magnetogenesis to work, something must break this conformal invariance. The electromagnetic field must be coupled to other fields or modified in some way that allows it to respond to the stretching of space-time. Several mechanisms have been proposed to accomplish this coupling. One approach involves coupling the electromagnetic field to the inflaton, the hypothetical field responsible for driving cosmic inflation itself. As the inflaton field changes during inflation, it could modify the properties of electromagnetic fields in ways that make them susceptible to being stretched and amplified. This coupling might arise naturally in certain theories of quantum gravity or extra dimensions. Another possibility involves modifications to the fundamental structure of electromagnetism at very high energies. Some theories suggest that at the extreme energy scales present during inflation, electromagnetic fields might behave differently than they do in the low-energy world we observe today. These modifications could provide the necessary breaking of conformal invariance. String theory, which attempts to unify all fundamental forces, including gravity, offers additional mechanisms for inflationary magnetogenesis. In string theory, electromagnetic fields can be coupled to other fields in ways that don't exist in conventional physics. Some string theory models predict that cosmic inflation could naturally generate primordial magnetic fields through these exotic couplings. The predicted strength of magnetic fields from inflationary magnetogenesis depends critically on the details of how conformal invariance is broken. Different models predict field strengths ranging from incredibly weak, perhaps 10 to the minus 20 Gauss, to moderately strong, around 10 to the minus 9 Gauss. For comparison, Earth's magnetic field is about half a Gauss, so even the strongest predictions from inflation represent extremely weak fields. These predicted field strengths might seem disappointingly small, but they could be sufficient to seed the cosmic dynamos that operate in galaxies and galaxy clusters. Modern astrophysical simulations suggest that even incredibly weak primordial fields, if they exist on large enough scales, can be amplified by factors of millions or billions through dynamo processes operating over cosmic time. The beauty of inflationary magnetogenesis lies in its ability to create magnetic fields that are coherent over enormous distances. Because the quantum fluctuations that seeded these fields originated from a tiny region of space that was subsequently inflated, the resulting magnetic fields would show correlations across scales much larger than anything that could be produced by conventional astrophysical processes. These large-scale correlations could provide a unique observational signature of inflationary magnetogenesis. If primordial magnetic fields from inflation exist, they should show patterns of correlation across distances of hundreds of millions of light-years or more. Such correlations would be almost impossible to explain through any other mechanism. Current observational efforts to detect inflationary magnetic fields focus primarily on their effects on the cosmic microwave background radiation. This ancient light, emitted when the universe was only 380,000 years old, carries information about conditions in the early universe. Primordial magnetic fields would have influenced the polarization patterns of this radiation in subtle but potentially detectable ways. The European Space Agency's Planck satellite, which operated from 2009 to 2013, provided the most sensitive measurements of cosmic microwave background polarization to date. While Planck didn't definitively detect signatures of primordial magnetic fields, it placed important constraints on their possible strength and distribution. Future experiments, including ground-based telescopes and possibly new space missions, may have the sensitivity needed to detect the extremely subtle signatures that inflationary magnetic fields would leave in the cosmic microwave background. These observations represent one of the few ways we might ever obtain direct evidence for the physics of cosmic inflation itself. Inflationary magnetogenesis also connects to some of the deepest questions in fundamental physics. The mechanism that breaks conformal invariance to allow magnetic field generation might be related to the physics responsible for the matter-antimatter asymmetry of the universe, the nature of dark matter, or the unification of fundamental forces. Some theoretical models suggest that the same processes that generate primordial magnetic fields during inflation might also produce other observable consequences, such as gravitational waves or exotic particles. If multiple signatures from the same underlying physics could be detected, it would provide powerful confirmation of inflationary magnetogenesis and the broader theoretical framework that supports it. The current status of inflationary magnetogenesis can best be described as promising but unproven. The theoretical framework is well developed and mathematically sophisticated. The mechanism is plausible within our current understanding of quantum field theory and cosmology, but definitive observational evidence remains elusive. This doesn't mean the theory is wrong, only that the observational signatures are extremely subtle and require extraordinary sensitivity to detect. The magnetic fields predicted by most inflationary models are so weak that they would be completely overwhelmed by fields generated later through astrophysical processes. Detecting them requires separating the primordial component from much stronger galactic and intergalactic fields. Despite these observational challenges, inflationary magnetogenesis remains one of the most compelling explanations for how magnetic fields could have originated in the early universe. It connects the quantum world to cosmic scales in a beautiful and mathematically elegant way. It provides a mechanism for generating the seed fields that cosmic dynamos could later amplify into the strong magnetic fields we observe today. Most importantly, inflationary magnetogenesis represents a purely physical explanation for cosmic magnetism. No external agents, no mysterious sources, no violations of known physics are required. Just the interplay between quantum mechanics, general relativity, and the extreme conditions that existed during the first moments of cosmic history. Whether this elegant theory accurately describes how magnetism first emerged in our universe remains to be determined. But the very fact that such a mechanism is possible within our current understanding of physics demonstrates that the origin of cosmic magnetic fields, while still mysterious in its details, is ultimately a natural consequence of the fundamental laws that govern our cosmos. Imagine watching water freeze in slow motion. At first, the liquid moves freely, molecules dancing randomly in all directions. Then, as temperature drops past the freezing point, something remarkable happens. The chaotic motion suddenly organizes into rigid crystal structures. Patterns emerge from randomness. Order crystallizes from chaos. This transformation from one state of matter to another is called a phase transition, and similar processes shaped the early universe in ways that could have given birth to the first magnetic fields. But the phase transitions that occurred in the infant cosmos were far more fundamental than water turning to ice. Instead of molecules rearranging themselves, the basic forces of nature themselves underwent dramatic transformations. The electromagnetic force, the weak nuclear force, the strong nuclear force, and gravity, which today appear as distinct and separate phenomena, may have once been unified into a single, all-encompassing interaction. As the universe cooled from its initial state of unimaginable heat, these unified forces underwent a series of phase transitions, breaking apart into the separate forces we observe today. Each transition was like a cosmic crystallization event, where the smooth, symmetric laws of physics suddenly developed the irregular structures and asymmetries that define our present universe. The most significant of these transitions for magnetic field generation occurred approximately 10 to the minus 12 seconds after the Big Bang, when the temperature of the universe dropped to about 100 billion degrees Celsius. At this moment, the electroweak force, which had unified electromagnetism, and the weak nuclear force underwent a phase transition that separated these interactions into the distinct forces we know today. To understand how this phase transition could generate magnetic fields, we need to delve into the strange world of quantum field theory. In this framework, what we perceive as empty space is actually filled with invisible fields that permeate every corner of the universe. These fields, like the Higgs field that gives particles their mass, have preferred values they want to settle into, much like a ball rolling down a hill seeks the lowest point. During the electroweak phase transition, the Higgs field underwent a dramatic change in its preferred value. Before the transition, the field maintained a value of 0 throughout space, preserving the symmetry between electromagnetic and weak forces. But as the universe cooled, this symmetric state became unstable, like a pencil balanced on its point, eventually falling to one side. The Higgs field began rolling away from 0 toward its new, lower energy configuration. But this transition didn't happen uniformly across all of space. Instead, different regions of the universe underwent the transition at slightly different times and in slightly different ways. This created a patchwork of regions where the Higgs field had different values and orientations. The boundaries between these regions, called domain walls, became sites of intense physical activity. Along these boundaries, the changing Higgs field created temporary imbalances between different types of particles. Electrons and positrons, normally created in equal numbers, might be produced in unequal amounts in these transition regions. Quarks and antiquarks could experience similar imbalances. These particle imbalances translated directly into electric charge imbalances. If more electrons than positrons were created in a particular region, that region would develop a net negative charge. If more positrons than electrons appeared elsewhere, those regions would become positively charged. These charge separations created electric fields, and as the boundaries between domains moved and evolved, these electric fields changed with time. According to Maxwell's equations, changing electric fields automatically generate magnetic fields. The moving domain boundaries during the electroweak phase transition created exactly the kind of time varying electric fields needed to produce magnetism. For the first time in the universe's history, organized magnetic fields could emerge from pure physics, without requiring any pre-existing magnetic seeds. The magnetic fields generated by the electroweak phase transition would have been incredibly weak by today's standards, perhaps 10 to the minus 20 Gauss, or even weaker, but they possessed a crucial advantage over magnetic fields generated by later astrophysical processes. They were created coherently across enormous volumes of space, potentially spanning regions that would later become entire galaxy clusters. This coherence arose because the phase transition occurred when the universe was still very small and dense. Regions that are now separated by millions of light years were once in close contact, able to influence each other's behavior. The magnetic fields created during the phase transition would therefore show correlations across vast distances, a signature that might still be detectable today. But the electroweak phase transition was not the only cosmic crystallization event that could have generated magnetic fields. Earlier in the universe's history, at approximately 10 to the -5 seconds after the Big Bang, another fundamental transition occurred. This was the quantum chromodynamics, or QCD phase transition, when quarks and gluons, previously existing as free particles, became permanently confined inside protons and neutrons. Before the QCD phase transition, the universe was filled with a quark-gluon plasma, a soup of fundamental particles interacting through the strong nuclear force. As the universe cooled and the temperature dropped below about 2 trillion degrees Celsius, this plasma underwent a dramatic reorganization. Quarks and gluons could no longer exist as isolated particles, but became bound together in composite particles like protons and neutrons. This transition, like the electroweak phase transition, created domain boundaries and particle imbalances that could generate electric and magnetic fields. The QCD transition was even more violent than the electroweak transition, involving the complete restructuring of matter from its most fundamental level. Some theoretical models suggest this transition could have produced stronger magnetic fields than the electroweak case. The physics of these phase transitions involve some of the most advanced concepts in modern theoretical physics. The mathematical description requires quantum field theory, statistical mechanics, and general relativity all working together. Computer simulations of these processes push the limits of our most powerful supercomputers, and even then can only approximate the true complexity of what occurred. One particularly intriguing aspect of phase transition magnetogenesis is its connection to other cosmic mysteries. The same processes that generate magnetic fields during phase transitions might also be responsible for the matter-antimatter asymmetry of the universe. In the very early cosmos, matter and antimatter should have been created in exactly equal amounts, leading to complete annihilation and a universe containing only radiation. The fact that we exist, made of matter rather than antimatter, indicates that some process in the early universe created a slight excess of matter over antimatter. This process, called baryogenesis, might be intimately connected to the same phase transitions that generated primordial magnetic fields. The particle imbalances that create magnetic fields could also be responsible for the matter-antimatter imbalance. Recent discoveries in particle physics have added new possibilities for phase transition magnetogenesis. The detection of the Higgs boson at the Large Hadron Collider in 2012 confirmed many aspects of our understanding of the electroweak phase transition. But measurements of the Higgs boson's properties suggest the transition might have been more complex than previously thought. Some models now propose that the electroweak phase transition occurred in multiple stages, with intermediate phases that don't exist in the universe today. These more complex transition scenarios could generate stronger magnetic fields and create more distinctive observational signatures. They might also connect to theories of dark matter and extra dimensions that extend our understanding of fundamental physics. The observational consequences of phase transition magnetogenesis are subtle but potentially detectable. Unlike magnetic fields generated by astrophysical dynamos, primordial fields from phase transitions should show no correlation with the distribution of matter in the universe. They were created before stars, galaxies, or even atoms existed, so their patterns should be independent of the cosmic web of dark matter and ordinary matter we observe today. These primordial fields might have influenced the formation of the first stars and galaxies in ways that left permanent signatures in the cosmic structure we observe. Computer simulations suggest that even very weak magnetic fields present during early star formation could affect how gas clouds collapsed and fragmented, potentially changing the masses and properties of the first stellar generation. The cosmic microwave background radiation again provides our best hope for detecting evidence of phase transition magnetogenesis. The magnetic fields would have influenced the motion of charged particles when the universe became transparent, leaving subtle imprints in the polarization patterns of the ancient light. Future experiments with greater sensitivity than current instruments might be able to detect these extremely faint signatures. Phase transition magnetogenesis represents a particularly elegant solution to the problem of cosmic magnetic field origins because it relies entirely on well-established physics. The existence of phase transitions in the early universe is not controversial. We know they occurred because we can see their consequences in the fundamental forces and particles that exist today. The prediction that such transitions could generate magnetic fields follows naturally from Maxwell's equations and quantum field theory. What remains uncertain is the strength and scale of the magnetic fields these transitions could produce. Different theoretical models predict vastly different outcomes, ranging from fields so weak they would be completely negligible to fields strong enough to significantly influence cosmic structure formation. Resolving these uncertainties requires both better theoretical understanding and more sensitive observational techniques. The beauty of phase transition magnetogenesis lies in its inevitability. If the universe underwent the phase transitions that particle physics tells us must have occurred, then magnetic fields were almost certainly generated as a natural consequence. The alternative would require remarkable fine-tuning to prevent magnetic field generation during these cosmic crystallization events. This mechanism also provides a natural explanation for why magnetic fields appear to be ubiquitous in the universe. From galaxies to galaxy clusters to the vast filaments of the cosmic web, magnetism seems to appear wherever we look with sufficient sensitivity. Phase transition magnetogenesis could provide the universal seeds that later astrophysical processes amplified into the diverse magnetic phenomena we observe today. Whether phase transitions in the early universe actually generated the seed fields for cosmic magnetism remains an open question. But the theoretical framework is solid, the physics is well understood, and the predictions are testable with future observations. Like cosmic inflation, phase transition magnetogenesis demonstrates that the origin of magnetic fields can be understood through natural physical processes operating under extreme conditions without invoking any mysterious or supernatural causes. Among all the proposed mechanisms for generating the first magnetic fields in the universe, one stands out for a remarkable quality. Unlike the exotic physics of cosmic inflation or the extreme conditions of phase transitions, the Biermann battery effect operates through processes we can observe, measure, and recreate in laboratories here on Earth. This mechanism for magnetic field generation is not theoretical speculation, but experimentally verified physics that happens wherever hot plasma exists under the right conditions. The Biermann battery effect was first described theoretically by German physicist Ludwig Biermann in 1950. Biermann was studying the behavior of ionized gases in stellar atmospheres when he discovered that magnetic fields could arise spontaneously from plasma under surprisingly common conditions. What he found was a fundamental process that requires no pre-existing magnetic field, no exotic particles, and no modifications to the laws of physics. The key insight behind the Biermann battery lies in understanding how electrons and ions behave differently in hot plasma. When matter is heated to extreme temperatures, atoms become ionized, their electrons stripped away to create a mixture of free electrons and positively charged atomic nuclei. This ionized gas, or plasma, makes up over 99% of all visible matter in the universe. In most situations, electrons and ions in plasma move together, maintaining overall electrical neutrality. But under certain conditions, these two types of particles can be pushed in different directions, creating electric currents that generate magnetic fields. The Biermann battery exploits a subtle but important difference between how electrons and ions respond to pressure and temperature gradients. Electrons, being much lighter than atomic nuclei, are more easily accelerated by pressure differences. When a pressure gradient exists in plasma, perhaps caused by a shock wave or gravitational compression, electrons respond more quickly than the heavier ions. This differential response creates a temporary separation of positive and negative charges, establishing an electric field. But the Biermann battery requires more than just pressure gradients to operate effectively. It also needs temperature gradients that are misaligned with the pressure gradients. When temperature varies in a different direction than pressure, electrons and ions can be pushed in different directions simultaneously. Electrons might be accelerated by the pressure gradient toward one direction, while being pushed by the temperature gradient in a perpendicular direction. This misalignment creates a more complex pattern of charge separation that generates electric currents flowing in organized loops rather than simple straight lines. According to Ampere's law, any electric current automatically produces a magnetic field circling around the current path. The Biermann battery converts the thermal and pressure energy of plasma into organized current flows, which then generate magnetic fields. The mathematical description of the Biermann battery involves the concept of vorticity in fluid dynamics. Vorticity measures how much a fluid is rotating or swirling at any given point. In plasma physics, the interaction between pressure gradients and temperature gradients can generate vorticity in the motion of charged particles. This vorticity directly translates into magnetic field generation through the fundamental equations of plasma physics. What makes the Biermann battery particularly relevant to the early universe is that the required conditions naturally existed in the primordial plasma that filled space before stars and galaxies formed. The early universe was far from uniform. Tiny density fluctuations, perhaps originating from quantum fluctuations during cosmic inflation, created regions of slightly higher and lower density throughout space. These density variations led to pressure differences as gravity began pulling matter toward the denser regions. At the same time, the cooling universe created temperature gradients as different regions lost heat at different rates. The combination of pressure gradients from gravitational collapse and temperature gradients from cooling provided exactly the conditions needed for the Biermann battery to operate. Computer simulations of structure formation in the early universe consistently show that Biermann battery processes would have generated magnetic fields during the collapse of the first gas clouds that eventually became galaxies and stars. As primordial gas clouds contracted under their own gravity, shock waves formed at the boundaries between infalling material and the gas already present in the cloud cores. These shock waves created the pressure and temperature gradients necessary for Biermann battery operation. The simulations predict that magnetic fields with strengths of around 10 to the minus 20 Gauss could have been generated through this process. While incredibly weak by terrestrial standards, these fields were strong enough to provide seeds for the cosmic dynamos that would later amplify them by factors of millions or billions. The Biermann battery has been observed and studied extensively in laboratory plasma experiments. Researchers at facilities like the National Ignition Facility in California and the Omega Laser Facility in New York have created conditions similar to those in stellar interiors and supernova. In these experiments, powerful lasers heat small targets to temperatures of millions of degrees, creating plasma with strong pressure and temperature gradients. When researchers measure the magnetic fields generated in these laboratory plasmas, they consistently find evidence of Biermann battery operation. The measured field strengths and patterns match theoretical predictions with remarkable accuracy. This experimental validation gives scientists confidence that the Biermann battery operates as predicted under the extreme conditions that existed in the early universe. Astrophysical observations also provide evidence for Biermann battery processes in action. When massive stars explode as supernovae, they create some of the most extreme shockwaves in the universe. These explosions drive fast-moving material into the surrounding interstellar medium, creating exactly the kind of pressure and temperature gradients that power the Biermann battery. Observations of supernova remnants using radio telescopes reveal complex magnetic field structures that appear to have been generated by Biermann battery processes. The magnetic fields show patterns that correlate with the shockwave structures, exactly as predicted by theory. Similar processes operate in the jets of material ejected by black holes and in the collision regions where galaxy clusters merge. One of the most compelling aspects of the Biermann battery is its universality. Wherever plasma exists with pressure and temperature gradients, this mechanism can generate magnetic fields. It doesn't require special conditions, exotic physics, or carefully tuned parameters. It's a natural consequence of the basic properties of ionized matter interacting with fluid dynamics. This universality explains why magnetic fields appear to be present throughout the universe, from individual stars to entire galaxy clusters. Wherever astronomers look with sufficient sensitivity, they find magnetic fields. The Biermann battery provides a mechanism that could have seeded magnetism in every cosmic environment where plasma physics operates. However, the Biermann battery does have significant limitations when it comes to explaining the strong magnetic fields we observe in galaxies today. While the mechanism can certainly generate seed fields, these seeds are typically too weak to account for the microgauss strength fields found in spiral galaxies like the Milky Way. The battery can provide the initial spark, but additional amplification mechanisms are needed to explain observed field strengths. This limitation doesn't diminish the importance of the Biermann battery in cosmic magnetogenesis. Instead, it highlights the multi-stage nature of magnetic field evolution in the universe. The battery generates weak seed fields during the early stages of structure formation. Later, as gas clouds collapse to form galaxies and stars, dynamo processes powered by rotation and turbulence amplify these seeds into the strong fields we observe today. The timing of Biermann battery operation in cosmic history is particularly significant. Unlike inflationary magnetogenesis or phase transition mechanisms that operated in the universe's first moments, the Biermann battery became active during the era of structure formation, roughly a few 100 million years after the Big Bang. This was when the first gas clouds began collapsing under gravity to form the ancestors of today's galaxies. At this epoch, the universe had cooled enough for atoms to form, ending the era when all matter existed as ionized plasma. But the gas clouds collapsing to form the first stars were dense enough to become ionized again through gravitational heating and early stellar radiation. This created the plasma conditions necessary for Biermann battery operation. Recent theoretical work has explored how the Biermann battery might have operated during even earlier epochs in cosmic history. Some models suggest that the mechanism could have been active during the recombination era, when electrons and protons first combined to form neutral hydrogen atoms. The complex dynamics of this transition might have created the pressure and temperature gradients needed for magnetic field generation. Other studies have investigated whether Biermann battery processes could operate during reionization, the epoch when the first stars and galaxies began emitting enough radiation to ionize the neutral hydrogen that filled space. The boundaries between ionized and neutral regions could have provided the gradient conditions necessary for magnetic field generation on very large scales. The observational signatures of Biermann battery magnetogenesis are more subtle than those predicted for inflationary or phase transition mechanisms. Because the battery operates during structure formation, the magnetic fields it generates are naturally correlated with the distribution of matter in the universe. This makes them harder to distinguish from fields generated later by conventional astrophysical dynamos. However, detailed studies of magnetic field patterns in galaxy clusters and individual galaxies might reveal signatures of Biermann battery origin. Computer simulations predict that primordial fields generated by the battery should show specific correlations with shockwave patterns and gas density distributions that differ from fields generated purely by dynamo processes. The Biermann battery also connects to broader questions about the role of magnetic fields in cosmic structure formation. Weak seed fields generated during early gravitational collapse could have influenced how gas clouds fragmented to form the first stars. Magnetic pressure and tension can resist gravitational collapse and affect the masses and formation rates of early stellar populations. Some theories suggest that differences in magnetic field strength during early structure formation could help explain why some regions of the universe contain mostly large galaxies, while others are dominated by smaller systems. The magnetic fields generated by Biermann battery processes might have created a form of cosmic feedback that influenced the entire subsequent evolution of structure in the universe. Modern magnetohydrodynamic simulations now routinely include Biermann battery processes when modeling galaxy formation and evolution. These simulations show that the battery consistently generates seed fields that are then amplified by rotational dynamos as galaxies develop. The combination of Biermann battery seeding followed by dynamo amplification provides a complete picture of how weak primordial fields could evolve into the strong galactic magnetism we observe today. The Biermann battery represents perhaps the most conservative and well-established mechanism for generating primordial magnetic fields. It requires no modifications to known physics, no exotic conditions beyond what certainly existed in the early universe, and no fine-tuning of parameters. It operates through processes we can study experimentally and observe astronomically. While the Biermann battery alone cannot explain the full strength of cosmic magnetic fields, it provides a crucial link in the chain of magnetic field evolution. It bridges the gap between the purely theoretical mechanisms that might have operated in the universe's first moments and the well-understood dynamo processes that operate in galaxies and stars today. The battery demonstrates that magnetic field generation is not a rare or exotic process, but a natural consequence of plasma physics operating under common astrophysical conditions. Wherever hot, ionized matter exists with appropriate pressure and temperature gradients, magnetic fields will spontaneously emerge. This universality helps explain why magnetism appears to be a fundamental feature of cosmic structure at all scales. The story of cosmic magnetism doesn't end with the generation of weak seed fields in the early universe. In fact, it barely begins there. Whether these primordial fields emerged from quantum fluctuations during inflation, phase transitions in the cooling cosmos, or Biermann battery processes during structure formation, they all shared one crucial characteristic. They were incredibly weak, perhaps 10 to the minus 20 Gauss, or even weaker, millions of times feebler than Earth's magnetic field. Yet when we observe galaxies today, we find magnetic fields with strengths measured in microgauss, roughly 1,000,000 times stronger than these predicted seed fields. The spiral arms of the Milky Way are threaded with magnetic fields strong enough to influence the motion of charged cosmic ray particles across thousands of light years. Galaxy clusters, the largest gravitationally bound structures in the universe, contain magnetic fields that extend across millions of light years. How did such weak seeds grow into the robust magnetic fields we observe throughout the cosmos? The answer lies in one of the most powerful and ubiquitous processes in astrophysics, the dynamo effect. Cosmic dynamos are natural machines that convert the kinetic energy of moving plasma into magnetic field energy, amplifying weak seed fields by factors of millions, billions, or even more over cosmic time. The fundamental principle behind all dynamo processes is surprisingly simple. When electrically conducting fluid moves through a magnetic field, it generates electric currents. These currents, according to Ampere's law, produce their own magnetic fields. Under the right conditions, these newly generated fields can be stronger than the original field that created them, leading to exponential amplification over time. This positive feedback process requires two essential ingredients that are abundant throughout the universe: rotation and turbulence. Rotation stretches and twists magnetic field lines, while turbulence folds and tangles them in complex ways. Together, these motions can transform a weak, disorganized magnetic field into a strong, coherent one through a process that operates like a cosmic amplifier with its gain turned up to maximum. To understand how cosmic dynamos work, consider what happens inside a spiral galaxy, like our own Milky Way. The galaxy rotates differentially, meaning that stars and gas clouds closer to the center complete their orbits faster than those farther out. This differential rotation acts like a cosmic taffy puller, stretching any magnetic field lines that thread through the galactic disk. Initially, a weak seed field might point in some random direction through the galaxy, but as differential rotation takes hold, the field lines get wound up by the galaxy's rotation. After just one rotation period, roughly 200 million years for the Milky Way, field lines that once pointed straight across the galaxy have been twisted into loose spirals. After several rotation periods, they form tight spirals that trace the galaxy's spiral arm structure. This stretching process, known as the omega effect after the Greek letter used to represent rotation rate in the equations, can amplify magnetic field strength significantly. Each time a field line gets stretched by a factor of 2, its magnetic strength doubles. Over many rotation periods, this stretching can increase field strength by enormous factors. But stretching alone isn't enough to create a sustainable dynamo. Without additional processes, the stretched and twisted field lines would eventually become so tangled that they would cancel each other out. This is where turbulence enters the picture, providing the second essential ingredient for dynamo action. Turbulence in galactic gas arises from many sources. Massive stars explode as supernovae, creating powerful shock waves that stir up the surrounding medium. Stellar winds from hot, luminous stars push against the interstellar gas. Gas falling into the galaxy from intergalactic space creates instabilities and mixing. All of these processes generate turbulent motions on scales ranging from individual star-forming regions to entire spiral arms. Turbulent motions can twist and fold magnetic field lines in ways that regenerate the original field configuration needed for continued stretching. This regeneration process, called the alpha effect, works by creating helical motions in the plasma that can convert twisted, tangled magnetic fields back into large-scale, organized structures. The combination of differential rotation and turbulent regeneration creates what astronomers call an alpha-omega dynamo. The omega effect stretches field lines through differential rotation, amplifying their strength. The alpha effect uses turbulent helicity to regenerate the field geometry needed for continued stretching. Together, these processes can sustain exponential magnetic field growth over many rotation periods. Computer simulations of galactic dynamos show that this process can amplify seed fields by factors of 10 to the 6th power or more over the lifetime of a galaxy. A primordial field of 10 to the minus 20 Gauss could grow to microgauss strength through dynamo action, exactly matching the field strengths observed in spiral galaxies today. The timescale for this amplification depends on the strength of differential rotation and turbulence in the galaxy. In actively star-forming galaxies with rapid rotation and vigorous turbulence, dynamo amplification can occur in just a few 100 million years. In more quiescent systems, the process might take several billion years to reach saturation. Galactic dynamos don't just amplify magnetic fields, they also organize them into coherent structures. Observations of spiral galaxies reveal that their magnetic fields often follow the spiral arm patterns, creating beautiful cosmic versions of the field patterns you might see around a bar magnet. These organized field structures arise naturally from the interplay between rotation, turbulence, and magnetic forces. But galactic dynamos are just one type of cosmic magnetic amplification machine. Similar processes operate in stars, where convection and rotation combine to generate the magnetic fields we observe in stellar atmospheres. Our Sun's 11-year magnetic cycle results from a dynamo process operating in the solar interior, where differential rotation and convective turbulence continuously regenerate the solar magnetic field. Stellar dynamos can be even more efficient than galactic ones, because stars are more compact and rotate more rapidly than galaxies. The Sun's magnetic field reaches strengths of thousands of Gauss in sunspot regions, amplified from whatever weak seed field existed when the solar system formed 4.5 billion years ago. At the largest scales, galaxy cluster dynamos operate across millions of light years. These vast systems contain hot, ionized gas with temperatures of tens of millions of degrees. The gas moves in complex patterns driven by galaxy mergers, gravitational interactions, and feedback from supermassive black holes. These motions can stretch and amplify magnetic fields across the entire cluster volume. Recent observations using radio telescopes have revealed magnetic fields throughout galaxy clusters, with strengths typically around 1 microgauss. These cluster magnetic fields show evidence of being amplified by dynamo processes, with field strengths that correlate with the level of turbulence and merger activity in each cluster. The efficiency of cosmic dynamos means that almost any seed field, no matter how weak, can potentially be amplified to observable levels given sufficient time and appropriate conditions. This universality helps explain why magnetic fields appear to be present wherever astronomers look in the universe. From individual planets to entire galaxy clusters, dynamo processes can transform weak primordial seeds into the diverse magnetic phenomena we observe. Modern magnetohydrodynamic simulations now routinely model dynamo processes across cosmic time, from the first collapsing gas clouds that formed primordial galaxies to the mature spiral systems we see today. These simulations show that dynamo amplification is not just possible, but inevitable in any rotating, turbulent system of ionized gas. The simulations also reveal that different types of cosmic structures generate different magnetic field patterns through dynamo action. Elliptical galaxies, which lack the organized rotation of spiral systems, tend to produce more chaotic, tangled magnetic fields. Irregular galaxies with active star formation can generate very strong but disorganized fields. Galaxy clusters produce fields that trace the large-scale gas flows and merger patterns. One of the most remarkable features of cosmic dynamos is their ability to operate efficiently, even when starting from incredibly weak seed fields. Laboratory experiments and theoretical calculations show that dynamo processes can begin amplifying fields, even when the initial magnetic energy is trillions of times smaller than the kinetic energy of the fluid motions driving the dynamo. This extreme sensitivity to initial conditions means that almost any mechanism capable of generating even the weakest primordial magnetic fields could potentially seed the cosmic dynamos we observe today. Whether the seeds came from inflation, phase transitions, Biermann batteries, or some combination of these processes, dynamo amplification could transform them into the strong fields that thread galaxies and galaxy clusters. The study of cosmic dynamos has also revealed important connections between magnetic fields and other astrophysical phenomena. Magnetic fields can influence star formation by providing additional pressure support against gravitational collapse. They can channel the flow of cosmic rays, affecting the chemical evolution of galaxies. They can even influence the formation of galactic spiral arms and bars. Recent observations have shown that magnetic fields may play a crucial role in regulating star formation efficiency across different types of galaxies. Galaxies with stronger magnetic fields tend to form stars more slowly, suggesting that magnetic pressure helps support gas clouds against gravitational collapse. This magnetic regulation of star formation could help explain why different galaxies have such different properties and evolutionary histories. Cosmic dynamos also connect to some of the most energetic phenomena in the universe. The jets ejected by supermassive black holes at the centers of galaxies appear to be collimated and accelerated by magnetic fields generated through dynamo processes in the accretion disks surrounding these black holes. Similarly, the explosive outflows from gamma-ray bursts may be powered and directed by magnetic fields amplified to extreme strengths through rapid dynamo action. The observational study of cosmic dynamos has been revolutionized by advances in radio astronomy and computational modeling. Modern radio telescopes can map magnetic field structures in galaxies and galaxy clusters by measuring the polarization of synchrotron radiation emitted by high-energy electrons spiraling around magnetic field lines. These observations reveal that cosmic dynamos are not just theoretical possibilities, but active, ongoing processes that continue to shape magnetic field evolution throughout the universe. Young galaxies show evidence of developing magnetic field structures as their dynamos spin up. Mature galaxies display the complex, organized field patterns expected from fully developed dynamo action. The success of cosmic dynamos in explaining observed magnetic field strengths and patterns provides strong support for scenarios where weak primordial seed fields are amplified to observable levels. Without dynamo amplification, it would be very difficult to explain how such strong magnetic fields could exist throughout the universe. Looking toward the future, improvements in observational techniques and computational power will allow astronomers to study cosmic dynamos in even greater detail. Next-generation radio telescopes will be able to map magnetic fields in distant galaxies, showing how dynamo processes operated when the universe was much younger. Advanced simulations will model dynamo action with unprecedented resolution and realism. These future studies will help determine which types of seed field generation mechanisms were most important in the early universe. By understanding how cosmic dynamos amplify different types of primordial fields, astronomers can work backward from today's observed magnetic field patterns to infer the properties of the seed fields that started the whole process billions of years ago. The story of cosmic dynamos demonstrates that the universe possesses natural mechanisms for transforming weak, disorganized magnetic seeds into the strong, coherent fields that play such important roles in cosmic evolution. These cosmic amplifiers ensure that even the faintest magnetic whispers from the early universe can grow into the magnetic symphonies that resonate throughout galaxies and galaxy clusters today. In our journey through the scientific understanding of cosmic magnetism, we've explored quantum fluctuations stretched by inflation, phase transitions in the cooling universe, plasma batteries generating currents from pressure gradients, and dynamos amplifying weak seeds into galactic powerhouses. These mechanisms represent the cutting edge of theoretical physics and observational astronomy, backed by mathematical rigor and experimental evidence. But alongside this legitimate science exists a shadow world of misconceptions, pseudoscientific claims, and outright myths about magnetic field origins. Understanding what cosmic magnetism is not proves just as important as understanding what it is. Misconceptions about magnetic field origins persist in popular culture, fringe theories, and even occasionally in scientific discussions where careful thinking gives way to speculative leaps. By examining and debunking these myths, we can better appreciate the elegant reality of how magnetism actually emerged in our universe. Perhaps the most persistent myth about cosmic magnetic fields is the idea that they appeared through some form of supernatural or magical intervention. This misconception stems from the undeniably mysterious nature of magnetism itself. Magnetic fields are invisible, can act across empty space, and seem to violate our everyday intuition about how objects influence each other. Ancient cultures often attributed magnetic phenomena to gods, spirits, or magical forces, and echoes of these beliefs persist today. Modern versions of this myth suggest that magnetic fields were somehow placed in the universe by external intelligences, divine intervention, or forces beyond the realm of natural science. Proponents of these ideas often point to the apparent fine-tuning of magnetic field strengths or the complex patterns observed in galactic magnetic fields as evidence of deliberate design. The reality reveals something far more remarkable than any supernatural explanation. The mechanisms we've explored, from quantum field theory to plasma physics, demonstrate that magnetic fields arise naturally from the fundamental laws of physics operating under extreme conditions. No external intervention is required. The apparent fine-tuning reflects the self-organizing properties of complex systems, where simple physical laws give rise to intricate patterns through purely natural processes. The mathematical beauty of Maxwell's equations, which describe all electromagnetic phenomena, shows that magnetism is woven into the very fabric of space-time. Electric and magnetic fields are different aspects of a single electromagnetic field, unified by the geometry of four-dimensional space-time. This unity emerged from the work of physicists like Faraday, Maxwell, and Einstein, who revealed that electromagnetic phenomena follow precise mathematical laws that require no mysterious external forces. Another common misconception involves the timing and sequence of magnetic field generation in cosmic history. Some popular accounts suggest that Earth's magnetic field was among the first to appear in the universe, providing a template or seed for magnetic fields elsewhere. This Earth-centric view reflects an outdated understanding of cosmic evolution and the relative timescales of different astrophysical processes. The truth is precisely the opposite. Cosmic magnetic fields on galactic and intergalactic scales formed billions of years before Earth even existed. Our planet formed roughly 4.5 billion years ago, but galaxies began developing magnetic fields when the universe was less than 1 billion years old. Galaxy clusters contain magnetic fields that predate our solar system by over 10 billion years. Earth's magnetic field, while locally important for protecting our atmosphere and enabling life as we know it, represents a relatively recent and minor addition to the cosmic magnetic landscape. Our planet's geodynamo is just one small example of the dynamo processes that operate throughout the universe on much larger scales and over much longer timescales. This misconception often leads to related errors about the relationship between planetary and cosmic magnetism. Some fringe theories propose that Earth's magnetic field somehow influences or controls magnetic fields in other galaxies, or that changes in cosmic magnetic fields directly affect Earth's geodynamo. While magnetic fields can indeed influence each other when they're in close proximity, the vast distances between cosmic structures make such interactions completely negligible. A particularly persistent myth involves the idea that magnetic fields appeared in the universe without any physical cause or mechanism. This spontaneous generation hypothesis suggests that magnetism simply materialized from nothing, without requiring moving electric charges or any other physical process. Sometimes this myth is dressed up in pseudoscientific language about quantum vacuum fluctuations or zero-point energy, but it fundamentally misrepresents how these quantum phenomena actually work. The reality is that every magnetic field that has ever been observed or predicted by theory can be traced to moving electric charges. This isn't just a convenient rule of thumb, but a fundamental law of electromagnetism that has never been violated. Even quantum vacuum fluctuations, which do create temporary electromagnetic fields, arise from the motion of virtual charge particles that pop in and out of existence according to the uncertainty principle. The mechanisms we've explored for primordial magnetic field generation all respect this fundamental principle. Inflation stretches quantum fluctuations that involve virtual charge particles. Phase transitions create particle imbalances that constitute moving charges. Biermann batteries generate currents through the differential motion of electrons and ions. In every case, magnetism emerges from the motion of electric charges, even if those charges exist only briefly or move in subtle ways. Some misconceptions about cosmic magnetism arise from misunderstanding the relationship between correlation and causation in astronomical observations. For example, astronomers have discovered that galaxy rotation curves, which measure how fast stars orbit around galactic centers, often correlate with magnetic field strength. Some alternative theories propose that magnetic fields are the primary cause of galaxy rotation, rather than the dark matter that mainstream astronomy invokes. While magnetic fields do exert forces on charged particles and can influence gas dynamics in galaxies, the energy contained in galactic magnetic fields is far too small to explain galaxy rotation curves. Magnetic pressure and tension forces are typically hundreds or thousands of times weaker than the gravitational forces that dominate galactic dynamics. Magnetic fields are a consequence of galactic rotation and turbulence, not their primary cause. This type of confusion between correlation and causation appears in many contexts related to cosmic magnetism. Because magnetic fields are generated by the same processes that drive other astrophysical phenomena, they naturally correlate with properties like rotation rate, turbulence level, and star formation activity. But correlation doesn't imply that magnetism is the driving force behind these other phenomena. Another category of misconceptions involves the strength and importance of magnetic fields compared to other cosmic forces. Popular accounts sometimes exaggerate the role of magnetism in cosmic evolution, suggesting that magnetic fields control galaxy formation, star formation, or even the expansion of the universe itself. While magnetic fields do play important roles in many astrophysical processes, they're typically much weaker than gravitational and thermal forces on large scales. The energy density in magnetic fields, even in the strongest galactic fields, is typically millions of times smaller than the energy density in dark matter or ordinary matter. Magnetic pressure in the interstellar medium is usually much smaller than gas pressure or turbulent pressure. Magnetic fields influence cosmic evolution primarily through their effects on charged particles and ionized gas, not through their direct gravitational or mechanical effects. This doesn't diminish the importance of cosmic magnetism, but it does place magnetic phenomena in proper perspective relative to other physical processes. Magnetic fields are crucial for understanding cosmic ray propagation, star formation efficiency, and the structure of interstellar gas. But they're not the dominant force shaping cosmic evolution on the largest scales. Some myths about magnetic field origins stem from misunderstanding the extreme conditions that existed in the early universe. Popular accounts sometimes suggest that the early cosmos was too chaotic or energetic for organized magnetic fields to form, implying that magnetism must have appeared later through more familiar astrophysical processes. In reality, the extreme conditions of the early universe were ideal for magnetic field generation through the mechanisms we've explored. High temperatures ensured that all matter existed as ionized plasma, providing the charged particles needed for electromagnetic phenomena. Rapid expansion during inflation could stretch quantum fluctuations to macroscopic scales. Phase transitions created the non-equilibrium conditions necessary for spontaneous current generation. The early universe wasn't too chaotic for magnetism. It was so energetic and dynamic that magnetic field generation was almost inevitable through multiple different mechanisms. The challenge isn't explaining how magnetic fields could form under such extreme conditions, but rather determining which of several possible mechanisms actually dominated. Misconceptions also arise about the observational evidence for different magnetic field generation mechanisms. Some popular accounts suggest that astronomers have definitively proven which mechanism generated the first cosmic magnetic fields, when in fact this remains an active area of research with competing theories and uncertain observational tests. The current state of the field is that several mechanisms are theoretically plausible and observationally consistent with what we know about cosmic magnetic fields. Future observations may eventually favor one mechanism over others, but for now, the origin of the first magnetic fields remains an open scientific question with multiple viable explanations. This uncertainty doesn't mean that scientists are simply guessing or that all proposed mechanisms are equally likely. The theoretical frameworks underlying inflation, phase transitions, and Biermann batteries are all based on well-established physics and make testable predictions. But the observational signatures are subtle and require extraordinarily sensitive measurements to detect. Perhaps the most dangerous misconception about cosmic magnetism is the idea that because some aspects remain mysterious or uncertain, the entire scientific approach must be wrong. This argument from ignorance suggests that any gaps in current knowledge prove that supernatural or pseudoscientific explanations must be correct. Science progresses precisely by identifying what we don't yet understand and developing better theories and observations to fill those gaps. The fact that we haven't definitively solved the problem of primordial magnetic field generation doesn't invalidate the scientific approach. Instead, it represents an exciting frontier where new discoveries await. The misconceptions we've examined often share common features. They tend to invoke mysterious forces or agencies rather than natural physical processes. They misrepresent the strength or importance of magnetic phenomena relative to other cosmic forces. They confuse correlation with causation or misunderstand the relationship between different physical processes. Most importantly, these misconceptions ignore the extraordinary success that scientific methods have achieved in understanding cosmic magnetism. We can explain magnetic fields in stars, planets, galaxies, and galaxy clusters through well-understood physical processes. We can reproduce many of these processes in laboratory experiments. We can make testable predictions about magnetic phenomena that are consistently confirmed by observations. The remaining mysteries about primordial magnetic field generation don't represent failures of science, but opportunities for deeper understanding. As observational techniques improve and theoretical models become more sophisticated, we're likely to resolve these questions through the same scientific methods that have already revealed so much about cosmic magnetism. The reality of cosmic magnetic field origins is far more fascinating than any myth or misconception. The idea that quantum fluctuations during cosmic inflation could seed magnetic fields across the observable universe stretches our imagination in ways that no supernatural explanation could match. The discovery that phase transitions in the fundamental forces could spontaneously generate magnetism reveals deep connections between particle physics and cosmology that are more profound than any magical intervention. Understanding what cosmic magnetism is not helps us appreciate what it actually is. A natural consequence of the fundamental laws of physics operating under the extreme conditions that existed in the early universe and continue to operate in cosmic environments today. The true story of magnetic field origins doesn't require mysterious external forces or violations of natural law. It emerges from the elegant mathematical relationships that govern electromagnetic phenomena and the complex dynamics of matter and energy in an evolving cosmos. The quest to detect primordial magnetic fields represents one of the most challenging observational problems in modern astronomy. These ancient fields, if they exist, would be incredibly weak by today's standards, buried beneath much stronger magnetic fields generated by conventional astrophysical processes, and detectable only through their subtle influences on phenomena that occurred billions of years ago. Yet scientists have developed ingenious methods to search for these ghostly remnants of the universe's magnetic birth, using some of the most sophisticated instruments and analytical techniques ever created. The primary challenge in detecting primordial magnetic fields lies in separating them from the magnetic fields generated later in cosmic history. When we observe a galaxy today, its magnetic field might contain contributions from multiple sources. Weak, primordial seeds, amplified by cosmic dynamos, fields generated by stellar processes, magnetism created during galaxy formation and mergers, and fields produced by ongoing astrophysical activity. Disentangling these components requires understanding how each type of magnetic field should behave and leave distinctive signatures in observable phenomena. The most promising approach for detecting primordial magnetism involves studying the cosmic microwave background radiation, the ancient light that has traveled to us from the early universe. This radiation was emitted roughly 380,000 years after the Big Bang, when the universe had cooled enough for electrons and protons to combine into neutral hydrogen atoms. Before this recombination epoch, the universe was opaque to light because free electrons scattered photons in all directions. After recombination, the universe became transparent, allowing light to travel freely through space. The cosmic microwave background carries information about conditions in the early universe encoded in tiny temperature variations across the sky. These temperature fluctuations, typically only a few hundred thousandths of a degree, reflect density variations in the primordial plasma that later grew into galaxies and galaxy clusters. But temperature isn't the only information contained in this ancient light. The polarization of cosmic microwave background photons provides an even more sensitive probe of early universe physics. Polarization occurs when light waves oscillate preferentially in certain directions rather than randomly in all directions. Sunlight reflecting off water or passing through polarized sunglasses demonstrates this phenomenon in everyday life. In the cosmic microwave background, polarization patterns arise from the motion of electrons in the primordial plasma just before recombination. If magnetic fields were present during this epoch, they would have influenced electron motions in ways that left distinctive imprints in the polarization patterns. Primordial magnetic fields would have created two types of signatures in cosmic microwave background polarization. First, they would have generated additional temperature fluctuations through their effects on plasma pressure and density. These magnetic contributions to temperature variations would have specific statistical properties that differ from fluctuations caused purely by gravitational processes. Second, magnetic fields would have created correlations between temperature fluctuations and polarization patterns that wouldn't exist in a universe without primordial magnetism. The European Space Agency's Planck satellite, which operated from 2009 to 2013, provided the most sensitive measurements of cosmic microwave background polarization achieved to date. Planck mapped the entire sky with unprecedented precision, measuring both temperature and polarization variations with accuracy sufficient to detect many subtle effects predicted by cosmological theory. While Planck didn't definitively detect signatures of primordial magnetic fields, it placed important constraints on their possible strength and distribution. The satellite's measurements showed that if primordial magnetic fields exist, they must be weaker than about 1 nanogauss on scales corresponding to galaxy clusters today. This upper limit is consistent with the predictions of most theoretical models for primordial magnetogenesis, but it's not yet sensitive enough to confirm or rule out any specific mechanism. Future cosmic microwave background experiments may have the sensitivity needed to detect primordial magnetic fields if they exist at the levels predicted by theory. Ground-based telescopes like the Simons Observatory and CMB Stage 4, currently under development, will measure polarization with even greater precision than Planck. Space-based missions being planned for the next decade could push sensitivity to even lower levels. But cosmic microwave background observations aren't the only way to search for primordial magnetism. Radio astronomy provides another powerful tool for probing ancient magnetic fields through their effects on high-energy particles called cosmic rays. These charged particles, mostly protons and heavier atomic nuclei, accelerated to nearly the speed of light, spiral around magnetic field lines as they travel through space. The paths that cosmic rays take from their sources to Earth depend on the magnetic fields they encounter along the way. Strong magnetic fields deflect cosmic rays significantly, while weak fields allow them to travel in nearly straight lines. By studying the arrival directions of cosmic rays from different parts of the sky, astronomers can map the magnetic field structures they encountered during their journeys. Ultra-high energy cosmic rays, with energies millions of times greater than anything produced in terrestrial particle accelerators, are particularly useful for probing large-scale magnetic fields. These extremely energetic particles can travel across cosmological distances while being deflected only slightly by weak magnetic fields. If primordial magnetic fields exist on the scales of galaxy superclusters, they should create detectable patterns in the arrival directions of these ultra-high energy particles. The Pierre Auger Observatory in Argentina and the Telescope Array in Utah represent the current generation of ultra-high energy cosmic ray detectors. These facilities use arrays of particle detectors spread across thousands of square kilometers to measure cosmic ray air showers, created when high-energy particles strike Earth's atmosphere. While these experiments haven't yet detected clear signatures of primordial magnetic fields, they're approaching the sensitivity needed to probe the magnetic field strengths predicted by theoretical models. Another approach to detecting primordial magnetism involves studying the magnetic fields in the most distant galaxies and galaxy clusters observable with current telescopes. Because light from these objects has traveled for billions of years to reach us, we're seeing them as they existed when the universe was much younger. The magnetic fields in these ancient systems might retain more direct signatures of their primordial origins before billions of years of galactic evolution obscured the initial conditions. Radio telescopes can measure magnetic field strengths in distant galaxies by observing synchrotron radiation, the light emitted by high-energy electrons spiraling around magnetic field lines. The intensity and polarization of this radiation depend on both the magnetic field strength and the energy distribution of the electrons producing it. By carefully analyzing these observations, astronomers can estimate magnetic field strengths in galaxies across cosmic time. Recent observations using the Very Large Array in New Mexico and the Atacama Large Millimeter Array in Chile have detected magnetic fields in galaxies seen when the universe was less than half its current age. Surprisingly, these ancient galaxies appear to have magnetic field strengths comparable to those in nearby galaxies, suggesting that cosmic dynamos operated efficiently even in the early universe. These observations don't directly prove the existence of primordial magnetic fields, but they do constrain the properties that any primordial seeds must have had. If weak primordial fields were amplified by cosmic dynamos to produce the strong fields observed in early galaxies, the dynamo process must have been remarkably efficient. This efficiency requirement helps narrow down the possible mechanisms for primordial field generation. Computer simulations play a crucial role in interpreting observations and predicting the signatures of different primordial magnetogenesis scenarios. Modern magnetohydrodynamic simulations can model the evolution of magnetic fields from the early universe through galaxy formation to the present day. These simulations allow scientists to predict what we should observe today if different types of primordial magnetic fields existed in the past. The most sophisticated simulations now include detailed models of cosmic inflation, phase transitions, Biermann battery processes, and dynamo amplification, all operating together in a consistent framework. By comparing the results of these simulations with observations of magnetic fields in galaxies, galaxy clusters, and the cosmic web, astronomers can test which combination of processes best explains the magnetic universe we observe. These computational studies have revealed that different primordial magnetogenesis mechanisms produce distinctive signatures that should be observable with sufficiently sensitive instruments. Magnetic fields from cosmic inflation should show very specific statistical properties and correlation patterns that differ from fields generated by phase transitions or plasma processes. The challenge is developing observational techniques sensitive enough to detect these subtle differences. One promising avenue involves studying magnetic fields in the cosmic web, the vast network of dark matter filaments that connects galaxies across the universe. Recent simulations suggest that primordial magnetic fields should survive in the low-density regions between galaxies, where they haven't been disrupted by star formation and galactic processes. These intergalactic magnetic fields might preserve more direct information about their primordial origins. Detecting magnetic fields in the cosmic web requires extremely sensitive radio observations of the faint synchrotron emission from this tenuous medium. Current radio telescopes are barely sensitive enough to detect the strongest predicted signals, but next-generation facilities, like the Square Kilometre Array, currently under construction in Australia and South Africa, should be able to map magnetic fields throughout the cosmic web with unprecedented detail. The Square Kilometre Array will be 50 times more sensitive than current radio telescopes and will be able to observe magnetic fields in distant galaxies, galaxy clusters, and intergalactic space with revolutionary precision. These observations should finally provide definitive tests of primordial magnetogenesis theories by measuring magnetic field properties across cosmic time and on all observable scales. Another exciting development involves using gravitational wave detectors to probe primordial magnetic fields. Strong magnetic fields in the early universe would have influenced the propagation of gravitational waves generated during cosmic inflation. Future gravitational wave observatories, more sensitive than current detectors like LIGO and Virgo, might be able to detect these subtle effects and provide completely independent evidence for primordial magnetism. The search for primordial magnetic fields also benefits from advances in laboratory plasma physics. Experiments at facilities like the National Ignition Facility can recreate some of the extreme conditions that existed in the early universe, allowing scientists to test theoretical predictions about magnetic field generation under controlled conditions. These laboratory studies provide crucial validation for the computer simulations used to interpret astronomical observations. Machine learning and artificial intelligence are increasingly important tools for analyzing the vast data sets produced by modern astronomical surveys. These techniques can identify subtle patterns in magnetic field observations that might indicate primordial origins, even when those patterns are too weak or complex for human researchers to recognize directly. The combination of improved observations, more sophisticated simulations, and advanced analysis techniques is bringing us closer to solving the mystery of primordial magnetic field origins. While definitive detection remains challenging, the rapid pace of technological development suggests that we may finally have answers within the next decade or two. The importance of detecting primordial magnetic fields extends far beyond understanding magnetism itself. These fields would provide unique probes of physics in the very early universe, potentially revealing information about cosmic inflation, phase transitions, and fundamental particle interactions that occurred under conditions impossible to recreate in terrestrial laboratories. If primordial magnetic fields are detected, they would represent fossil relics from the universe's first moments, preserved across billions of years of cosmic evolution. Like cosmic microwave background radiation, which provides our most direct observational window into the early universe, primordial magnetic fields would offer complementary information about conditions during epochs that are otherwise observationally inaccessible. The quest to detect these ancient magnetic ghosts represents one of the most technically demanding challenges in modern astronomy. But the potential rewards in terms of understanding fundamental physics and the origin of cosmic structure make this one of the most important frontiers in contemporary astrophysical research. Whether we ultimately detect primordial magnetic fields or place even more stringent limits on their properties. The results will significantly advance our understanding of how the magnetic universe came to be. Understanding how the first magnetic fields emerged in the universe might seem like an abstract intellectual exercise, relevant only to specialists studying exotic corners of theoretical physics. But the quest to explain primordial magnetogenesis connects to some of the most fundamental questions about the nature of reality itself. The mechanisms that generated cosmic magnetic fields operate at the intersection of quantum mechanics, general relativity, particle physics, and cosmology, offering unique windows into physics under the most extreme conditions imaginable. The study of primordial magnetic fields provides one of the few observational pathways for probing the physics of cosmic inflation, that remarkable epoch when the universe expanded faster than the speed of light during its first fraction of a second. While the basic framework of inflationary cosmology has achieved widespread acceptance among physicists, many details about how inflation actually worked remain mysterious. We don't know what field or particle drove the inflationary expansion, what determined when inflation ended, or exactly how the smooth, homogeneous post-inflationary universe developed the tiny fluctuations that later grew into galaxies and stars. Primordial magnetic fields could provide crucial clues about these deep questions. If magnetic fields were generated during inflation through the stretching of quantum fluctuations, their observed properties would reveal information about the inflaton field itself. The strength, scale, and statistical properties of inflationary magnetic fields depend on how the electromagnetic field coupled to the inflaton and how the expansion rate changed during the inflationary epoch. Different models of cosmic inflation make specific, testable predictions about the magnetic fields they should produce. Some models predict fields that are coherent across enormous scales, while others generate fields with more complex correlation patterns. Some predict fields that are nearly scale invariant, maintaining similar strengths across different size scales, while others produce fields with significant scale dependence. By measuring the properties of primordial magnetic fields through their effects on the cosmic microwave background or other observable phenomena, astronomers could distinguish between competing inflationary models in ways that aren't possible through other observations. This would represent a remarkable achievement, using magnetic field observations to probe physics that occurred during the universe's first 10 to the minus 30 seconds. The connection between magnetic fields and inflation also illuminates fundamental questions about the nature of electromagnetic fields themselves. In our everyday experience, electromagnetic phenomena seem completely separate from gravitational effects. But during cosmic inflation, electromagnetic fields and space-time geometry were intimately connected through the extreme curvature and rapid expansion of space itself. Understanding how electromagnetic fields behave under such extreme gravitational conditions requires extending our theories beyond the regimes where they've been experimentally tested. This theoretical exploration helps physicists develop more complete theories that unify electromagnetic and gravitational phenomena, potentially pointing toward a quantum theory of gravity that has eluded scientists for decades. Phase transitions in the early universe offer another pathway for connecting primordial magnetogenesis to fundamental physics. The electroweak phase transition, which separated electromagnetic and weak nuclear forces roughly 10 to the minus 12 seconds after the Big Bang, represents one of the most important events in cosmic history. This transition gave mass to fundamental particles through the Higgs mechanism and established the structure of forces that govern particle interactions today. The magnetic fields generated during the electroweak phase transition depend sensitively on the details of how this transition occurred. Was it a smooth, gradual change or a violent first-order phase transition involving bubbles of the new phase expanding through space? Did the transition proceed at exactly the same rate everywhere, or were there regional variations that created more complex patterns? These questions connect directly to some of the most important unsolved problems in particle physics. The nature of the electroweak phase transition affects calculations of the matter-antimatter asymmetry that explains why the universe contains matter rather than pure radiation. It influences predictions for the production of gravitational waves that might be detectable by current or future gravitational wave observatories. It even relates to the stability of the Higgs boson itself and whether our current vacuum state is truly stable or merely long-lived. Observations of magnetic fields generated during the electroweak phase transition could provide experimental information about these fundamental questions. By measuring the strength and correlation properties of phase transition, magnetic fields, physicists could constrain the dynamics of the Higgs field under the extreme conditions that existed in the early universe. The study of primordial magnetism also connects to the broader program of precision cosmology, where increasingly accurate observations are used to test theoretical predictions and discover new physics. Just as measurements of the cosmic microwave background have revealed dark matter, dark energy, and the detailed parameters of our cosmological model, observations of primordial magnetic fields could uncover new aspects of fundamental physics. For example, some theories predict that primordial magnetic fields should be coupled to the dark sector of the universe, the mysterious dark matter and dark energy that make up 95% of the cosmic energy budget. If such couplings exist, magnetic field observations could provide indirect information about dark matter particle properties or the nature of dark energy. The connection between magnetism and dark physics becomes particularly intriguing when considering modified theories of gravity. Some alternatives to general relativity predict that electromagnetic fields should behave differently in the presence of dark matter or dark energy. These modifications could leave distinctive signatures in primordial magnetic field generation or evolution that would be observable today. Primordial magnetogenesis also illuminates the deep connections between different fundamental forces. In our current understanding, electromagnetic, weak nuclear, and strong nuclear forces are believed to be different aspects of a single unified interaction that existed at very high energies. This grand unification program represents one of the most ambitious goals in theoretical physics, seeking to understand all non-gravitational forces as manifestations of a single underlying symmetry. The magnetic fields generated during phase transitions in the early universe depend on how these unified forces broke apart as the universe cooled. The timing, strength, and patterns of magnetic field generation provide observational tests of grand unified theories that are impossible to perform in terrestrial particle accelerators, which can't reach the extreme energies where unification occurs. Some grand unified theories predict specific relationships between magnetic field generation and other phenomena like proton decay, neutrino masses, or the production of magnetic monopoles. If primordial magnetic fields are detected with properties that match these theoretical predictions, it would provide strong support for particular unification scenarios. The quest to understand primordial magnetism has also driven important advances in computational physics and numerical methods. Simulating magnetic field evolution from the early universe to the present day requires solving some of the most complex partial differential equations in physics, involving the coupled dynamics of plasma, magnetic fields, gravity, and turbulence across enormous ranges of space and timescales. These computational challenges have spurred the development of new numerical algorithms, more efficient computer codes, and innovative approaches to parallel computing. The techniques developed for magnetohydrodynamic simulations have found applications in many other areas of physics and engineering, from fusion energy research to weather prediction to industrial plasma processing. The study of cosmic magnetism has also contributed to our understanding of complex systems and emergent phenomena. The magnetic fields we observe in galaxies today emerged from the complex interplay of many different physical processes operating across billions of years. Understanding how this complexity arose from simpler initial conditions provides insights into how ordered structures can emerge spontaneously from chaotic systems. This understanding has applications far beyond astrophysics. The same mathematical techniques used to study magnetic field evolution help scientists understand how patterns form in biological systems, how markets evolve in economics, and how information spreads through social networks. The study of cosmic magnetism contributes to the broader interdisciplinary science of complexity and emergence. Primordial magnetogenesis also connects to experimental physics through its relationship to laboratory plasma studies. Many of the processes that generated magnetic fields in the early universe, such as the Biermann battery effect and various plasma instabilities, can be recreated and studied in controlled laboratory environments. These experiments provide crucial tests of theoretical predictions and help validate the computer simulations used to model cosmic magnetic field evolution. The connection between laboratory and cosmic plasma physics has led to productive collaborations between astrophysicists and fusion energy researchers. Techniques developed for controlling magnetic fields in fusion reactors inform our understanding of cosmic dynamos, while insights from astrophysical magnetism help improve laboratory plasma confinement schemes. Looking toward the future, the study of primordial magnetism promises to remain at the forefront of fundamental physics research. Next-generation particle accelerators may be able to recreate some of the extreme conditions that existed during early universe phase transitions, providing direct experimental tests of magnetogenesis mechanisms. More powerful computers will enable increasingly realistic simulations of magnetic field evolution across cosmic time. New theoretical frameworks that unify quantum mechanics and general relativity may predict novel mechanisms for primordial magnetic field generation that haven't been considered yet. String theory, loop quantum gravity, and other approaches to quantum gravity all make predictions about electromagnetic phenomena under extreme conditions that could be tested through magnetic field observations. The detection of primordial magnetic fields would also have profound implications for our understanding of causality and information transmission in the universe. These fields would represent information about conditions in the very early universe that has been preserved across billions of years of cosmic evolution. Like cosmic microwave background photons, primordial magnetic fields would be messengers from epochs that are otherwise completely inaccessible to direct observation. The study of how information is encoded in primordial magnetic fields and how it survives the complex evolution of cosmic structure connects to fundamental questions about the nature of information itself. These questions are increasingly important in physics, from black hole information paradoxes to the role of information in quantum mechanics and thermodynamics. Perhaps most importantly, the quest to understand primordial magnetism exemplifies the deep unity underlying all of physics. The same quantum field theory that describes particle interactions in accelerators also governs electromagnetic field evolution during cosmic inflation. The same general relativity that explains planetary orbits also determines how space-time expansion affects magnetic field generation. The same plasma physics that powers fusion reactors also operated in the primordial universe. This unity suggests that understanding any one aspect of physics deeply enough will eventually illuminate all the others. The study of cosmic magnetic field origins, while seemingly specialized, actually touches on nearly every major area of modern physics. It demonstrates how phenomena that appear completely unrelated, from quantum mechanics to cosmology to plasma physics, are actually different facets of a single, elegant theoretical framework. The importance of primordial magnetogenesis for fundamental physics extends far beyond the specific question of how the first magnetic fields formed. It represents a unique laboratory for testing our most advanced theories under conditions that can never be recreated on Earth. It provides observational windows into epochs of cosmic history that are otherwise completely inaccessible, and it demonstrates the remarkable power of physics to connect phenomena across the entire range of scales and energies that exist in our universe. Whether or not we ultimately detect primordial magnetic fields, the theoretical framework developed to understand their generation has already advanced our knowledge of fundamental physics in ways that will benefit science for generations to come. The quest to explain cosmic magnetism continues to push the boundaries of human knowledge about the deepest workings of nature itself. Despite decades of theoretical development and increasingly sophisticated observations, the scientific community has not yet reached consensus on how the first magnetic fields emerged in the universe. This might seem surprising given the remarkable progress that has been made in understanding cosmic magnetism and the elegant theoretical frameworks that have been developed to explain primordial magnetogenesis. But the persistent lack of consensus reflects the extraordinary difficulty of observing phenomena that occurred billions of years ago under conditions that existed only briefly in cosmic history. The current state of the field resembles the situation in cosmology during the 1970s and 80s, when multiple competing theories attempted to explain the large-scale structure of the universe. At that time, scientists had developed sophisticated models for how galaxies and galaxy clusters could form through gravitational collapse, but they lacked the observational precision needed to distinguish between different scenarios. It took revolutionary advances in telescope technology and computational modeling to finally establish the standard model of cosmology that we accept today. Primordial magnetogenesis faces similar challenges. The theoretical frameworks are mathematically sophisticated and physically plausible. Computer simulations can model magnetic field evolution with impressive detail and accuracy, but the observational signatures of different magnetogenesis mechanisms are often subtle, requiring extraordinary precision to detect and distinguish from one another. Consider the challenge of separating primordial magnetic fields from those generated later by conventional astrophysical processes. When we observe a galaxy today, its magnetic field represents the cumulative result of billions of years of complex evolution. Weak primordial seeds may have been amplified by cosmic dynamos, but they've also been mixed, stretched, and reorganized by galactic rotation, stellar feedback, and merger events. Disentangling the primordial component from this complex evolutionary history requires understanding all of these processes with remarkable precision. This is further complicated by the fact that different magnetogenesis mechanisms can produce similar observable consequences through different physical pathways. For example, both inflationary magnetogenesis and phase transition mechanisms can generate magnetic fields with similar strengths and correlation properties, even though they operate through completely different physics. Distinguishing between these scenarios requires measuring extremely subtle differences in statistical properties or correlation patterns. The observational challenges are compounded by the inherent weakness of primordial magnetic fields. Even the strongest theoretical predictions suggest that these fields were billions of times weaker than the magnetic fields we can easily measure in laboratories or around nearby astronomical objects. Detecting such weak fields requires pushing observational techniques to their absolute limits and developing new methods that can probe magnetism with unprecedented sensitivity. Current observations are tantalizingly close to the sensitivity needed to detect primordial magnetic fields, but they haven't quite reached the threshold where definitive detections become possible. The Planck satellite placed important upper limits on primordial field strength through cosmic microwave background observations. But these limits are still about an order of magnitude above the strongest theoretical predictions. Future experiments may close this gap, but they require technological advances that are only now becoming feasible. The theoretical landscape is further complicated by the fact that multiple magnetogenesis mechanisms could have operated simultaneously in the early universe. Cosmic inflation, phase transitions, and Biermann battery processes all had the potential to generate magnetic fields, and there's no fundamental reason why only one mechanism should have dominated. If multiple processes contributed to primordial magnetism, separating their individual contributions becomes an even more challenging observational and theoretical problem. Different theoretical models also make predictions that span enormous ranges of magnetic field strength and correlation length. Inflationary models, depending on how the electromagnetic field couples to the inflaton, can predict anything from completely negligible fields to fields strong enough to significantly influence cosmic structure formation. Phase transition models show similar variation, with predictions depending sensitively on details of the transition dynamics that are difficult to constrain experimentally. This theoretical uncertainty reflects our incomplete understanding of the extreme physics that operated in the very early universe. While the basic frameworks of inflation, phase transitions, and plasma physics are well established, applying them to the unprecedented conditions of the primordial cosmos requires extrapolating far beyond the regimes where these theories have been experimentally tested. For example, inflationary magnetogenesis requires understanding how electromagnetic fields behave when space-time itself is expanding faster than the speed of light and when energy densities exceed anything achievable in terrestrial experiments. Phase transition magnetogenesis depends on the detailed dynamics of symmetry breaking in quantum field theories under conditions of extreme temperature and density that existed only briefly in cosmic history. The computational challenges involved in modeling these processes add another layer of complexity to the theoretical debate. Realistic simulations of magnetic field evolution from the early universe to the present day require enormous computational resources and sophisticated numerical techniques. Even the most advanced simulations must make approximations and simplifications that could affect their conclusions. Different research groups often use different computational approaches, leading to results that can be difficult to compare directly. Some simulations focus on very early epochs, with high precision but limited dynamic range, while others model longer evolutionary periods with less detailed physics. Reconciling the results from different computational approaches requires careful analysis and often reveals additional sources of uncertainty. The interdisciplinary nature of primordial magnetogenesis research also contributes to the ongoing debate. Understanding cosmic magnetic field origins requires expertise in quantum field theory, general relativity, plasma physics, astrophysics, and cosmology. Researchers from these different fields sometimes approach the same problems with different assumptions, methodologies, and interpretative frameworks. For instance, particle physicists working on inflationary models might focus primarily on the quantum field theory aspects of magnetic field generation, while astrophysicists studying galactic evolution might emphasize the later amplification and organization of these fields by dynamo processes. Integrating these different perspectives into a coherent picture requires extensive collaboration and communication across disciplinary boundaries. The observational astronomy community faces its own set of challenges in constraining primordial magnetogenesis theories. Different types of observations, from cosmic microwave background studies to radio astronomy to cosmic ray measurements, provide complementary but sometimes apparently contradictory information about cosmic magnetic fields. Radio observations might suggest that magnetic fields in high redshift galaxies are stronger than expected from some theoretical models, while cosmic microwave background studies place stringent upper limits on primordial field strength. Reconciling these different observational constraints requires understanding the systematic uncertainties and selection effects that affect each type of measurement. The rapid pace of technological development in observational astronomy also means that the observational landscape is constantly evolving. New telescopes and instruments regularly provide data with unprecedented sensitivity and resolution, sometimes confirming previous results, but occasionally revealing unexpected phenomena that require theoretical reinterpretation. This dynamic situation makes it difficult for theoretical models to keep pace with observational capabilities. By the time a theoretical prediction has been thoroughly developed and tested through simulations, new observational results may have already shifted the empirical landscape in ways that require theoretical adjustments. The scientific culture and sociology of different research communities also influence how the magnetogenesis debate unfolds. Some research groups focus intensively on particular theoretical mechanisms, developing increasingly sophisticated models and predictions within specific frameworks. Others take broader, more comparative approaches that attempt to evaluate multiple scenarios simultaneously. These different research styles can lead to apparent disagreements that reflect methodological differences as much as genuine scientific disputes. Researchers who have invested heavily in developing particular theoretical models may naturally emphasize the successes of their approaches, while being more critical of competing scenarios. The peer review process in scientific publishing can also contribute to the fragmentation of the field. Different journals and review panels may have preferences for particular types of theoretical approaches or observational methods. This can lead to the development of somewhat isolated research communities that don't interact as extensively as might be ideal for resolving complex, interdisciplinary questions. International collaboration and communication are crucial for making progress on primordial magnetogenesis, but they face practical challenges related to funding structures, career incentives, and institutional priorities. Large-scale theoretical and observational projects require sustained support over many years, but funding agencies often prefer shorter-term projects with more immediate deliverables. The education and training of young researchers also plays a role in shaping the field's evolution. Students entering the field must master an enormous range of theoretical and observational techniques, from quantum field theory to numerical simulation to radio astronomy data analysis. The time required to develop expertise across such a broad range of areas can slow the pace at which new ideas are developed and tested. Despite these challenges, there are reasons for optimism about resolving the primordial magnetogenesis debate in the coming years. Observational capabilities are improving rapidly, with next-generation telescopes and instruments approaching the sensitivity needed to detect primordial magnetic field signatures. The Square Kilometre Array, Cosmic Microwave Background Stage 4 experiments, and advanced gravitational wave detectors all promise to provide new types of data relevant to understanding cosmic magnetic field origins. Theoretical understanding is also advancing through improved computational methods and more sophisticated analytical techniques. Machine learning and artificial intelligence are beginning to be applied to the analysis of complex simulation data and observational data sets, potentially revealing subtle patterns that human researchers might miss. The increasing recognition of primordial magnetogenesis as a key unsolved problem in cosmology is also leading to more coordinated research efforts. International collaborations are forming to tackle specific aspects of the problem, from theoretical modeling to observational planning to data analysis. Perhaps most importantly, the field is benefiting from improved communication between different research communities. Conferences and workshops increasingly bring together particle physicists, cosmologists, plasma physicists, and observational astronomers to discuss magnetogenesis from multiple perspectives. This cross-fertilization of ideas is helping to identify the most promising theoretical scenarios and observational strategies. The current lack of consensus on primordial magnetogenesis should not be viewed as a failure of the scientific method, but rather as a reflection of the extraordinary difficulty and importance of the problem. The universe's magnetic origins involve some of the most extreme physics imaginable, operating under conditions that existed only briefly in cosmic history and leaving signatures that are barely detectable with current technology. The fact that multiple plausible mechanisms have been identified for generating primordial magnetic fields demonstrates the creativity and sophistication of modern theoretical physics. The development of observational techniques sensitive enough to potentially detect these ancient fields showcases the remarkable capabilities of contemporary astronomy and instrumentation. As observations become more sensitive and theoretical understanding becomes more refined, the scientific community will eventually converge on a consensus picture of how cosmic magnetism began. This consensus may reveal that a single mechanism dominated primordial field generation, or it may show that multiple processes contributed in ways that we're only beginning to understand. Either outcome would represent a major advance in our understanding of fundamental physics and cosmic evolution. The resolution of the primordial magnetogenesis debate will not only explain how magnetic fields originated, but will also provide new insights into the physics of the very early universe, the nature of cosmic phase transitions, and the complex processes that shaped the cosmic structures we observe today. After exploring the quantum fluctuations of cosmic inflation, the phase transitions that separated fundamental forces, the plasma currents of Biermann batteries, and the cosmic dynamos that amplified weak seeds into galactic powerhouses, we arrive at a remarkable conclusion. The first magnetic fields in the universe emerged not through supernatural intervention or mysterious external forces, but through the elegant operation of natural physical laws under the most extreme conditions imaginable. This conclusion represents one of the most profound achievements of modern theoretical physics and observational astronomy. We have traced the origin of cosmic magnetism back to the universe's earliest moments, revealing how the invisible threads that connect galaxies and guide cosmic evolution first came into existence through processes we can understand, model mathematically, and in some cases even recreate in laboratory experiments. The story begins with a fundamental principle that has never been violated in any observation or experiment. Magnetic fields always arise from electric charges in motion. This simple statement, encoded in Maxwell's equations over a century and a half ago, provides the unifying thread that connects all mechanisms for primordial magnetic field generation. Whether we consider quantum fluctuations stretched by inflationary expansion, particle imbalances created during phase transitions, or pressure-driven currents in primordial plasma, every proposed mechanism ultimately relies on the motion of electric charges to generate magnetism. The early universe provided ideal conditions for such charge motion to occur. In the hot, dense plasma that filled space before atoms could form, electrons and atomic nuclei moved freely without the constraints that limit electromagnetic phenomena in the cooler cosmos we observe today. Temperature gradients, pressure differences, phase boundaries, and quantum fluctuations all had the potential to create organized motions of these charged particles, generating the first magnetic fields through well-understood physical processes. Three primary mechanisms have emerged from decades of theoretical research as the most plausible explanations for primordial magnetogenesis. Each operates through different physics and at different epochs in cosmic history, but all represent natural consequences of known physical laws applied to the extreme conditions of the early universe. Inflationary magnetogenesis offers perhaps the most elegant explanation, connecting magnetic field origins directly to the exponential expansion that occurred during the universe's first fraction of a second. If electromagnetic fields were coupled to the inflaton field that drove cosmic expansion, quantum fluctuations in these fields could have been stretched from microscopic to macroscopic scales, creating magnetic field patterns coherent across enormous distances. This mechanism requires breaking the conformal invariance that normally makes electromagnetic fields insensitive to space-time expansion. But several plausible theoretical frameworks can accomplish this coupling. String theory, modified gravity theories, and extensions of the standard model of particle physics all provide potential pathways for inflationary magnetic field generation. The predicted field strengths from inflation are typically very weak, perhaps 10 to the minus 20 Gauss or less, but they possess the crucial advantage of coherence across scales that would later become entire galaxy clusters. These large-scale correlations provide a potentially unique observational signature that could distinguish inflationary magnetism from fields generated through other mechanisms. Phase transition magnetogenesis operates through different physics, but offers equally compelling explanations for primordial field generation. As the universe cooled and fundamental forces separated from their initial unified state, domain boundaries formed where different regions underwent transitions at different times or in different ways. These boundaries created temporary particle imbalances that generated electric currents and consequently magnetic fields. The electroweak phase transition, which separated electromagnetic and weak nuclear forces roughly 10 to the minus 12 seconds after the Big Bang, provides the most thoroughly studied example of this mechanism. The dynamics of symmetry breaking during this transition depend on fundamental properties of the Higgs field and could generate magnetic fields with strengths and correlation patterns that reflect the underlying particle physics. Similar processes could have operated during other phase transitions in the early universe, including the QCD transition that confined quarks and gluons into protons and neutrons. Each transition represents a cosmic crystallization event where the smooth, symmetric laws of high-energy physics developed the irregular structures that characterize our present universe. The Biermann battery effect stands apart from these exotic mechanisms by relying entirely on conventional plasma physics that can be observed and studied in terrestrial laboratories. When plasma experiences pressure gradients in one direction and temperature gradients in a different direction, the differential response of electrons and ions creates electric currents that automatically generate magnetic fields. The beauty of the Biermann battery lies in its universality and experimental verification. The mechanism operates wherever the appropriate gradient conditions exist, requiring no exotic physics or fine-tuned parameters. Laboratory experiments at facilities around the world have confirmed the theoretical predictions for Biermann battery operation, providing confidence that the same processes could have operated in the early universe. While individually too weak to explain the strong magnetic fields observed in galaxies today, Biermann battery fields could have provided crucial seeds during the epoch of structure formation, when the first gas clouds began collapsing to form the ancestors of present-day galaxies. The amplification of these weak primordial seeds into the strong magnetic fields we observe today occurs through cosmic dynamos, perhaps the most thoroughly understood aspect of cosmic magnetogenesis. These natural amplification machines convert the kinetic energy of rotating, turbulent plasma into magnetic field energy, operating through processes that are observed throughout the universe. Galactic dynamos can amplify seed fields by factors of millions or billions over cosmic timescales, transforming the weakest primordial whispers into the micro-Gauss strength fields that thread spiral galaxies like the Milky Way. The combination of differential rotation and turbulent regeneration creates a positive feedback process that sustains exponential magnetic field growth until the amplified fields become strong enough to react back on the plasma motions that created them. Similar dynamo processes operate in stars, galaxy clusters, and other cosmic environments wherever rotating plasma exists. The universality of dynamo amplification explains why magnetic fields appear throughout the cosmic hierarchy, from individual planets to the largest structures in the universe. Current observational capabilities are approaching the sensitivity needed to detect direct signatures of primordial magnetic fields through their effects on the cosmic microwave background radiation, the statistical properties of cosmic structure, and the propagation of high-energy particles across cosmological distances. While definitive detection remains challenging, the rapid pace of technological development suggests that answers may come within the next decade or two. The theoretical framework for understanding primordial magnetogenesis continues to evolve as our knowledge of fundamental physics advances. New insights from particle accelerator experiments, gravitational wave detections, and precision cosmological observations regularly inform and refine our models of early universe physics. Perhaps most importantly, the study of cosmic magnetic field origins demonstrates that even the most mysterious aspects of our universe can be understood through natural physical processes. The invisible magnetic threads that connect galaxies and influence cosmic evolution on the largest scales arose through the same fundamental laws that govern electromagnetic phenomena in our everyday experience. This represents a remarkable triumph of the scientific method and human intellectual achievement. We have traced phenomena that operate across billions of light years back to their origins in the quantum fluctuations and phase transitions of the universe's first moments. We have connected the most exotic conditions imaginable to physics we can study in terrestrial laboratories. The implications extend far beyond understanding magnetism itself. The mechanisms that generated primordial magnetic fields provide unique probes of physics under conditions that can never be recreated on Earth. They offer observational windows into cosmic inflation, phase transitions in quantum field theory, and the fundamental forces that shaped our universe. Whether primordial magnetic fields originated through quantum fluctuations during inflation, particle imbalances during phase transitions, plasma processes during structure formation, or some combination of these mechanisms, their existence would represent fossil relics from the universe's earliest epochs, like the cosmic microwave background radiation, which preserves information about conditions when the universe first became transparent. Primordial magnetic fields would carry information about physical processes that operated under the most extreme conditions in cosmic history. The quest to understand cosmic magnetic field origins also exemplifies the deep unity underlying all of physics. The same quantum mechanics that describes atomic structure also governs electromagnetic field fluctuations during inflation. The same statistical mechanics that explains phase transitions in terrestrial materials also describes the symmetry-breaking events that separated fundamental forces in the early universe. The same fluid dynamics that operates in Earth's oceans also drives the cosmic dynamos that amplify magnetic fields in galaxies. This unity suggests that understanding any aspect of physics deeply enough will eventually illuminate connections to all other areas of natural science. The study of cosmic magnetism, while seemingly highly specialized, actually touches on nearly every major branch of modern physics and provides insights that benefit our understanding of nature across all scales. The story of the first magnetic fields is ultimately a story about the power of physics to explain the most fundamental aspects of our universe through natural processes. From the quantum foam of the earliest moments to the vast magnetic highways that thread today's cosmic web, magnetism emerges as an inevitable consequence of the physical laws that govern matter, energy, space, and time. We live in a magnetic universe not because of external design or supernatural intervention, but because the fundamental properties of charged particles and electromagnetic fields operating under the extreme conditions of the early cosmos naturally give rise to the magnetic phenomena we observe. The invisible fields that surround us, from Earth's protective magnetosphere to the galactic magnetic arms that guide cosmic rays across thousands of light years, all trace their ancestry to those first primordial moments when physics itself was writing the magnetic signature of the cosmos. This scientific understanding represents one of humanity's greatest intellectual achievements, connecting the smallest quantum fluctuations to the largest cosmic structures through elegant mathematical relationships and observational discoveries. The magnetic universe reveals itself not as a mystery requiring supernatural explanation, but as a natural consequence of the beautiful, comprehensible laws that govern all of physical reality. The first magnetic fields emerge from the quantum heart of space-time itself, amplified by cosmic dynamos into the magnetic tapestry that shapes cosmic evolution today. In understanding their origins, we glimpse the profound connections between quantum mechanics and cosmology, between the infinitesimal and the infinite, between the first moments of time and the vast magnetic symphony that continues to play across the cosmos 13.8 billion years later. The first magnetic fields were subtle, born from quantum ripples and plasma currents in the universe's infancy. These primordial seeds, weaker than anything we can easily measure today, carried within them the potential to become the vast magnetic networks that now connect galaxies across billions of light years. From weak beginnings grew the magnetic webs that shape cosmic evolution, guide the paths of charged particles, and influence the birth of stars in spiral arms throughout the cosmos. We continue to search for definitive proof of how these ancient fields first emerged, using telescopes that peer back toward the cosmic dawn and computers that simulate the extreme physics of the early universe. The quest challenges our most sophisticated theories and pushes our observational capabilities to their absolute limits. Yet even without final answers, we can confidently say that the origin of cosmic magnetism is no impenetrable mystery requiring supernatural explanation. The story of the first magnetic fields is fundamentally a story of physics in its purest form. Whether they arose from quantum fluctuations stretched by cosmic inflation, from particle imbalances during phase transitions, or from plasma currents driven by pressure gradients, every proposed mechanism operates through natural processes that we can understand, model mathematically, and in many cases observe directly in laboratory experiments. These mechanisms reveal the deep connections between the smallest scales of quantum mechanics and the largest structures in the observable universe. They show how the fundamental forces of nature, operating under conditions of unimaginable extremity, naturally give rise to organized phenomena that persist across cosmic time. They demonstrate that even the most exotic aspects of our universe emerge from the elegant mathematical relationships that govern all of physical reality. The magnetic universe surrounds us not by accident or design, but as an inevitable consequence of how charged particles behave when matter exists as hot plasma under the influence of gravity, rotation, and the expanding space-time of an evolving cosmos. The invisible threads that connect distant galaxies and the protective field that shields our planet both trace their origins to the same fundamental principles, operating across vastly different scales, but united by the underlying physics of electromagnetism. In understanding how magnetism first sparked into existence, we glimpse something profound about the nature of the cosmos itself. We see a universe where complexity and beauty emerge naturally from simple laws, where quantum whispers can grow into galactic symphonies, and where the story of cosmic evolution is written in invisible magnetic ink across the sky. The first magnetic fields represent not just the beginning of cosmic magnetism, but a testament to the extraordinary power of physics to create order, structure, and wonder from the fundamental properties of space, time, matter, and energy.